Is there any disturbance in phone? Is there any disturbance in my voice in phone? Am I audible? Is there any disturbance? Okay, I will start the class. State space analysis of continuous systems. So, the state space analysis is a powerful and modern approach for the design and analysis of control systems. So, we already know the conventional and old method for the design and analysis of control system, which is the transfer function method. So we have discussed many topics on transfer function method. So transfer function method is an old method for the design and analysis of control systems. Am I audible? Is my voice clear? If there is any disturbance, just message me. My voice is not audible. So the state space analysis method is the powerful and it is the modern approach for the design and analysis of control systems. Okay, when compared to the transfer function method which we used to follow. So, what are all the drawbacks that this transfer function method have, because of which we don't want to design and analyze the control systems using this transfer function? Let us see the drawbacks. So, drawbacks are the the transfer function is defined under zero initial conditions. Okay, that is one of the drawback. And transfer function is applicable only to linear time invariant systems, and it is also applicable only to single input single output systems. And transfer function won't provide any information about the internal state of the system. Okay, transfer function won't provide any information about the internal state of the system. So since the transfer function does not means it is defined only under zero initial conditions, since it is applicable only to linear time invariant systems and single input single output systems, and it won't provide any information regarding internal state of the system. Okay, we go for the uh, modern approach of design and analysis of the control system, which is state space analysis. Okay, so let us see what are all the advantages that are available for state space analysis method, or we can even call it as state variable analysis. So the advantages are, I will take the laser. The advantages are it is applicable to both linear and non-linear systems. Okay, and it is also applicable to time variant and time invariant systems. It is applicable to multiple input and multiple output systems. This state variable analysis or state space analysis gives the idea about the internal state of the system, and initial conditions can be incorporated in the system design, state equations. Okay, so the state equations are highly compatible for simulation on analog as well as digital computers. Okay, So these are all the advantages of state variable analysis or state space analysis. Now let us see what is meant by this state of the system and state variable of the system. So let us see what is meant by state of the system and state variable of the system. So let us consider a system. This is our system. Let us assume the input to the system is R of t and output to the system is y of t. Okay? R of t is the input and y of t is the output. Okay? So here for this system, the output, it not only depends on the input that has been applied to the system at t greater than or equal to, it is t greater than or equal to t0, but also on the initial conditions of the system, that is at t equal to t0 or at t less than or equal to, I can say, okay, at t less than or equal to t0. So the output y of t, it not only depends on the input of the system at t greater than or equal to t0, but it also depends on the initial condition of the 0 immediately when you give the input, okay, or prior condition before even giving the input, what is the state of the system, okay, it depends on both. So the output y of t, it depends on, it has two factors, we can say, we can categorize into two factors. One is it is depending on the input at t equal to t0 and it is depending on the input at t greater than or equal to t0. Okay, so it not only depends, the output not only depends on the input at t greater than or equal to t0, but it also depends on the input at t equal to t0. Therefore y of t is equal to y of t at t equal to t0 and y of t at t greater than or equal to t0. So y of t is equal to, what is it? Y of t at t equal to t0 plus y of t at t greater than or equal to t0. So the first part, we can, it has two parts. Y of t has two parts now. Okay, y of t has two parts. So the first part, you can see, first part of output is what? Y of t at t equal to t0. So that means what prior state of the output not only depends on the present state, it also depends on the previous state of the system. So we can say the output is obtained at y of t at t equal to t0, means the output is obtained from minus infinity interval to t0 interval. So y of t, the interval at which the y of t is obtained, first part 1 is obtained, is from minus infinity to t0. Okay, so let us see the second part. The second part of the output, it is obtained at t greater than or equal to t0, means by this part 2 of this output, part 2 of the output will depend on the time interval, the output that is obtained for the time interval from t equal to 0 to t interval. Okay, so these are the two parts of the outputs. So you can rewrite it as y of t equal to y of t0 plus integral of 0 to t y of t. Okay. So the output will have two parts. One part is with respect to the initial condition, another part is after giving the input, output after giving the input. So just write it down, draw the diagram and write it down, and just draw the diagram, write down this title, state of the system and state variable, draw this diagram and write down the equations. As soon as you complete, inform. So here this y of t0 is what? It is the output at initial condition. So this output at initial condition, we can call it as state of the system. We can call it as what? State of the system. You can call it as, sorry, I was about to finish. You can call it as state of the system. So output at initial condition is known as what? State of the system. And output of this system consists of two parts. One at the initial state output, one output is at initial state, another output after giving the input from t equal to t0 to t. Okay, so the output at the initial state, part 1 output means output part, first part of the output, that is output at the initial condition is the state of the system. Okay, and the variables which represent the state of the system, okay, whichever variable represents the state of the system, that is known as state variable. Whichever variable represents the state of the system is known as state variable. So if you want, I can show you in another slide. See, the term y of t0 is known as state of the system, and the variable which represents the state of the system is known as state variable. The term y of t0, that is the output which is obtained at initial condition, is known as state of the system, and the variable that represents this state of the system is known as state variable. Now let us see what is meant by state. Okay, so what is meant by state? State is group of variables. Okay, state is a group of variables which summarize the history of the system in order to predict the output values. Okay, so state is a group of variables which summarize the history of the system in order to predict the output values. So in order to predict the output values, the history of the system is summarized, okay, by group of variables. Next, state variable. State variable is number of state variables required will be equal to the number of storage elements present in the system. Okay, state variables means it is the number of state variables that are required that will be always equal to the storage elements present in the system. So state variable means if there are storage elements in the given system such as inductor or capacitor, now when inductor is there, if current is flowing in the circuit because of this inductor, that current is our state variable. Okay, that current is our state variable. If you have a capacitor in the given circuit, then the voltage across the capacitive element, okay, voltage across the capacitive element, okay, that voltage, okay, this voltage, it is known as state variable. Okay, it is the state variable. So state variables will be always equal to number of storage elements. That means that if there are two storage elements, one inductor and one capacitor, then because of the inductor current will flow, okay, and because of the capacitor there will be voltage across the capacitive element. Therefore there will be a current flow is there as well as voltage across the capacitor is there. Therefore two state variables will be there in the given circuit if it is an LC circuit. Suppose there are two inductors, okay, two inductors are there, if there are two inductors in the given circuit, okay, if there are two inductors and one capacitor is there, okay, okay, there are two inductors and one capacitor, then because of these two inductors current will flow. So two state variables because of two inductors and one capacitor is there, so voltage across the capacitor will be there. So total three state variables will be there. Okay, so current in the circuit or voltage across the elements because of the storage elements is are known as the state variables. Okay, state variables are nothing but current flowing through due to the inductor and voltage due to the capacitor. Okay, they are the state variables. Now see, let us see state vector. State vector, it is a vector which contains the state variables as elements. Okay, whichever vector contains these state variables, currents or voltages, which are due to the storage elements in the circuit, those currents and voltages, if any vector consists of these variables, these currents or voltages, okay, that vector is known as state vector. So these currents and voltages are due to the storage elements in the given circuit. Okay, I hope you have understood what is meant by state variables. State variables are the currents or voltages in the given circuit because of the storage elements. Okay, and if any vector contains these state variables as elements, then that vector is known as state vector. Okay, so let us proceed further. Now let us discuss few more points on state variables. Let us consider a pure capacitive circuit. Yeah. So let us see the voltage across the capacitor as state variable. What did I say? The voltage in the circuit because of the capacitor is the state variable. So here you can see a single capacitor is there and this is the voltage across the capacitor. So this Vc of t is the state variable. How many state variables are there here? Only one state variable is there in this circuit, that is Vc of t. Now here, so here what is the current in this circuit? I of t is equal to C into dVc of t by dt. So what is Vc of t? 1 by C integral minus infinity to t I of t dt. Now here I have told you in state space analysis or state variable analysis, we must always consider the initial conditions also. That's why you must always consider the limit minus infinity to t. Okay, so you can divide this I of t because you can divide this integral part from for the initial condition separately and for the present condition you can separate it. So 1 by c integral of minus infinity to t naught I of t dt and 1 by c integral t naught to t I of t dt. Okay, so you can separate the present means for t less than t naught and for t equal to and greater than t naught condition. Okay, so to justify that condition you can do that. Okay, so what is our Vc of t now? 1 by c integral minus infinity to t naught I of t dt plus 1 by c integral t naught to t I of t dt. Now this whole part, this is voltage across the capacitor, this is also voltage across the capacitor. So this voltage you can denote it by some Vc of t naught and this voltage some Vc of t. Okay, so here Vc of t naught is the initial voltage across the capacitor. Okay, so the whatever voltage is there, this Vc of t is the state variable across the capacitor. Draw the circuit, write down equations. Meanwhile, I am explaining. It is better if people draw the circuit and write down the equations while I am explaining, so that our time will be saved. So let us see the current through the inductor. It can be taken as state variable. So here I have a pure only one inductive element is there. What is the voltage across inductor? VL of t, and current through this inductive element is I of t. So what is the voltage VL of t? We know the formula L into di of t by dt. So what is IL of dt? Current in the inductor 1 by L integral of 0 minus infinity to t. VL of t dt. So why we have considered minus infinity to t? We want to consider even the initial conditions. That's why. So now you can separate the initial condition and means initial condition means for t less than or equal to t naught, and you can separate for t greater than or equal to t naught. So if you separate those two voltages during those two conditions, then you will get cursor is here. Okay, so IL of t is equal to 1 by L integral of minus infinity to t naught VL of t dt plus 1 by L integral t naught to t VL of t dt. So this is also, this is our current IL of t naught, that is initial current, and IL t. Okay, so here, okay, this is our, one second. So this is our current ILT is the current through the inductor, which is our state variable. So this is our state variable. Okay, so I hope you have understood what is meant by state variable. State variable is the voltage or current in the circuit due to the storage elements. So the number of state variables will depend on number of storage elements. Okay, if 3 inductors and 2 capacitors are there, total state variables are 5. If 3 capacitors and 2 inductors are there, then also number of state variables is 5. So I hope you have written. If you have completed, inform. If you have not completed, okay then. Now let us see state space representation of the system. So state space representation of the system. Now let us consider multiple inputs and multiple output system. Okay, let us assume there are m number of inputs, p number of outputs, and n state variables. I hope you got the idea what is meant by state variables. Okay, so if you want me to repeat any topic, you just mention in the comment box so that I will repeat. So there are m number of inputs, p number of outputs, and n number of state variables. So where is my cursor? Here. So if there are m number of inputs, let us assume our input notation is u. So u1 of t, u2 of t, u3 of t up to um of t are our inputs. If there are p number of outputs, then let us assume our notation for output is y. So y1 of t, y2 of t, y3 of t up to p of t. And state variables notation, let us assume notation is x. Then our state variables are x1 of t, x2 of t up to xn of t. Okay, so notations for input is u, notation for output is y, and notation for state variable is x. So just write it down. we can represent this on the control system. So this is how you can represent it. This is our control system. These are our inputs. These are our outputs. Sorry. These are our outputs, and these are the state variables. Okay. So inputs, you can instead of writing all the inputs, you just denote it by single U. Outputs Y and variables X. Just draw it. Now, if you want to represent this these inputs, outputs, and the state variables in vector form, you can represent them in vector form. Let us see how you can represent. Let us see how you can represent. So see here, these are our inputs, isn't it? U of t. Where is it? That's it. Yeah. U of t. So what are our input variables? U1 of t, U2 of t, up to Um of t. So this is the vector representation of the input. Just write it down. Okay, I hope you have written. So output y of t, you can y of t if you want to represent it in vector form. So y of t is y1 of t to y2 of t up to yp of t. Okay, similarly state variable vector x of t is x1 of t, x2 of t up to xn of t. So we have written all this vector in matrix form. Just write it down. Okay. Now let us see the state equations and output equations. State equations and output equations. So we know what is meant by state variable now. So we can represent the state variable, okay, in the form of n number of first order differential equations. Okay, state variables can be represented in n number of first order differential equations. So we know state variables are denoted by x. So let us consider the first state variable x1 of t. So you just differentiate it with respect to time. If you differentiate it with respect to time, d by dt of x1 of t, I have not written here. Okay, so x1 of t or x1. So you can rewrite it as what? x1 dot. Okay, so it will be the state variable. It will be the function of set of the state variables. Okay, which are varying from 1 to n, and the input variables, okay, u1 to un. Okay, so state variables, the first order differential equation of each state variable will be the function of what? Function of set of all the state variables and the set of all the input variables. Okay. Similarly, second, if we differentiate the second state variable, that is x2 dot, it will also be function of all the set of all the input state variables and the input variables. Similarly, xn by d by dt of xn, that is first order differentiation of your state variable. It will also be function of all the state variables and the input variables. So you can but if you take the first order differentiation of the state variables, then they are the functions of the state variables as well as the input variables. So just write it down. Now, so instead of writing all those terms, just simply you can say x dot of t is equal to f of x of t u of t. Okay, or I can write based on what I have written earlier, x dot, okay, sorry, so instead of writing x dot of t, you can write like this: x dot is equal to f of so instead of writing like that, better I will end my show and I can write, I will take a text, I can write it here. So what is it? So you can rewrite it as x. So I will just copy it here. Okay, so you can write like this: x dot of t is equal to f of x of t u of t. Instead of writing that, you can even write like x dot is equal to f of x comma x f of x and u. Okay. Similarly, similar to your vector notation, output vector notation also you can write it down: y of t. Output y of t is also function of, okay, set of the state variables, okay, and the input variables. Okay, output is also function of set of state variables and input variables, similar to what? First order differential equation, okay, of the state variables. This is the first order differential equation of your state variables. It is the function of what? Set of all the state variables and the input variables. Similarly, output is also function of set of all the input variables and the state variables. Now let us see the state model of the linear system. State model of linear system. So So we have seen what's known by state equation. Okay, so actually state model of the given system or linear system, it will be consisting of two equations. One is state equation, other one is output equation. Okay, one is state equation, other one is output equation. Just now we have seen this is the vector notation. This is our state equation, output vector. This is our output equation. Okay, state equation. This is our state equation. This is our output equation. So state model consists of two equations. One is state equation, other one is output equations. Okay. So the state equation of any system is a function of state variables and inputs. Okay. State equation is the function of state variables and inputs. That's what we have seen earlier in this slide. This is our state equation, which is the function of what? State variables and inputs. X of t is state variable, u of t is the input. So that's the same thing. Okay, same equation. Function of state variables and the inputs. So for linear time invariant system, the first derivative of the state variables can be expressed as linear combination of state variables and inputs. Linear combination of what? State variables and inputs. So if we want to represent the first order derivative of state variables for a linear time invariant system, it is expressed like this. So this is the first order derivative of your state variable, x dot of 1. So that is equal to what? Some constant a11, okay, which is the coefficient of this variable x1, okay, a12, x2, and so on up to a1 and xn, plus the input variables. So b11 is some coefficient or constant term which is the coefficient of u1. So plus b12 u2 plus b1m un, and so on. x2 dash, x2 dot, sorry, not dash, the d by dt of x2. Okay, x2 dot means d by dt of x2 is equal to a21 x1 plus a22 x2 up to a2n xn plus b21 u1 plus b22 u2 plus up to b2m um. So this continues up to d by dt of xn, which is equal to an1 x1 plus an2 x2 up to ann xn plus bn1 u1 plus bn2 u2 plus up to bnm un, where the coefficients of these variables, that is for x or u, coefficients of u or x, they are the constants. Okay, they are the constants. So state model consists of what? State model consists of state equation, cursor. Yeah. State model consists of what? State equation and output equation. State equation is what? State equation is the function of, it is the function of state variables and inputs. Okay, state variables and inputs. So for a linear time invariant system, the first order derivative, this is the first order derivative, isn't it? First order derivative of state variables, okay, can be expressed as the functions of, okay, or in other words I can say the functions of state variables and inputs, or I can say can be expressed as the linear combination of state variables and inputs. So where's the cursor? This is the linear combination of inputs are, I'm sorry, variables and inputs. So just write it down. Just write it down. Now you can represent these state equations in matrix form. Okay, so you can represent all x1 dot x2 dot to xn dot. Okay, so first order derivatives of x state variables is equal to all the coefficients of your x state variables. Okay, so coefficients is my cursor, yeah. So these are all the first order derivatives of state variables, coefficients in one matrix, all the state variables in one matrix, all the coefficients of your inputs in one matrix, and the inputs in another matrix. So what is this? This whole matrix form, it can be segregated and written in one equation, that is x dot of t is equal to a x of t plus b u of t, which is our state equation. This is our state equation. So what is A? A is a state matrix of size n into n. Okay. B is an input matrix of size n into m. X of t is what? It is a state vector of size n into 1. And u of t is the input vector of size m into 1. You just compare this, whatever here I have written this, you just compare it with the above matrix, it will tell you. Okay. So remember, this is our state equation. This is our state equation. Just write it down quickly. If you are able to follow or not, just message me. Are you able to follow or not? Okay, then we have seen state equation. Let us see the output equation. Let us see the output equation. So output equation. So output of n at any time are the function of state variables and inputs. Okay, similar to your state equation, the output at any time, it will be function of state variables and inputs. Okay, hence the output variables, they can be expressed as linear combination of state variables and inputs. It is similar to your previous case. Okay, so output variables can be expressed as linear combination of state variables and inputs. See, you just observe only the notation of the constants, coefficients of the constants of your x has been changed. Earlier it was a, now it is c. And similarly, you just observe the coefficients of your inputs. Earlier it was b, now it is d. So here, no need to go for first order differential equation. Directly the output variables are expressed as the linear combination of state variables and inputs. So output variables are what? Y1 is equal to C11 x1 plus C12 x2 plus up to C1n xn. Okay, similar plus D11 u1 plus D12 u2 up to D1m u1. Similarly, y2 is equal to C21 x1 plus C22 x2 up to C2n xn plus D21 x u1 plus D22 u2 up to D2m um. So y varies from number of outputs are from 1 to p. To p number of outputs were there. So yp is equal to cp1 x1 plus cp2 x2 up to cpn xn plus dp1 u1 plus dp2 u2 up to dpm um. Okay, so where the C and D are the coefficients which are constants. Okay, just write it down. So I hope you have understood. So state model has two equations. One is state equation and other one is output equation. State equation, it is the first order differential term which is the function of the state variables and the inputs. Similarly, output equation, it is also function of state variables and the inputs. Write in short form and as quickly as possible. If you complete, we can proceed further. So you can once again, similar to your previous case, you can represent or you can represent these equations. Okay, so this linear equations in matrix form, similar to your previous case. So I will show you the matrix form. This is it. These are the outputs. These are the coefficients of the state variables. These are the coefficients of your input variables. Okay, so you can segregate all these matrices and you can write as y of t is equal to c x of t plus d ut. Okay, so this y of t, c x of t, dut is nothing but our output equation. So this is our output equation. Okay, where what is c? C is the output matrix of size p into n. D is the transmission matrix. Okay, D is known as transmission matrix of size p into m. X of t is what? State vector of size n into 1. Y of t is the output vector of size p into 1. U of t is the input vector of size m into 1. Okay, so just write it down quickly. Even if you are unable to write, you can later go through this video and write it down. Write down all this. Okay. So it's wastage of time if I ask you to write it down, write it down. So let us proceed further. I hope you are able to follow. So let us see the block diagram and signal flow graph for the state model. So what is state model? State model consists of a state equation and output equation. What is state equation? It is the first order differential equation of your state variable. So that is x dot of t. That is equal to what? A x of t plus b u of t. And what is output equation? Y of t equal to c x of t plus d u of t. Okay, so how to represent in block diagram? Let us see. Let us start with the input. Let us start with the input. What is our input? U of t is our input, isn't it? So let us consider u of t. Okay. So here what is it? V into u of t. So it is our input. Input is multiplied with the transfer function. We know that. Input is always multiplied with the gain. We can say gain. Okay. Instead of using the term transfer function, it is better to use the word gain. So B is the gain. So u of t into b. Okay, so just write down b in a block. Okay, since we have to represent in block diagram. So b into u of t. What is b into u of t? It has to be added with what? A into x of t to get x dot of t. To get x dot of t, it has to be added. So put a summing point here. Okay, put a summing point. Since you have to add, write plus plus. I will take the laser, I will erase and I will take the laser. Okay, put a summing point and write plus plus. So I have written here x dot of t because when you multiply these two and add with something else, you should get x dot of t, isn't it? You should get x dot of z. So to what it has to be added? A into x of t. So this is x dot of t. This is differentiation, d by dt of x of t. If you integrate it, differentiation and integration, they will cancel. What is left over? You will get x of t. Okay, just write a block here a and x of t must be multiplied with a and give it to the summing point. So what is it? X of t into a, u of t into b. Just add it, you will get x dot of t. Okay, I hope you have understood. Okay, it's very simple, very simple, nothing complicated. If you are listening, you will be able to understand easily. Okay, you will be able to easily understand. So now, another, let's go to the next equation, d u of t. So d has to be multiplied with u of t. Already here you have u of t is our input. So u of t is there. Just write it, draw a block here. So from u of t, just give connections, d into u of t plus c into x of t. Where is x of t? Already x of t is there. So put a block here and write c. So x of t into c you will get, u of t into d you will get. So they should be added together here. Plus is there. So put a summing point here. So c into x of t plus d into u of t. What is it? Y of t. So y of t is our output. So it's a very simple and easy block diagram. So this is the state model. It's a block diagram representation of your state model. So very easily you can represent it. So if you are able to draw the block diagram, so from the block diagram you can draw the signal flow graph. Okay, from the block diagram you can draw the signal flow graph. So simply wherever junctions are there or summing point is there or takeaway point or is there. Okay, so you just put the dot and just give the connections. You will get the signal flow graph. I hope you are able to follow. I hope you have understood block diagram. So from this, just put a dot here, put a dot here at this summing point, put a dot here, put a dot here, and just give signals. Just connect those dots, okay, and write the gain values above the connections. So if you write the gain values above the connections, you will get the signal flow graph. Just see here. This is our input. So gain value. So this is the dot. This is our so one of the summing point we can say, or here what I have considered here is yeah, x of t is x dot of t is besides to it, but here I have written x dot of t, x of t, and this is y of t. So u of t into b, you will get u of t into b plus a into x of t will is equal to x dot of t. Okay, so this is the integral. It's just simply you just go to this block diagram and just convert that into signal flow. It's very easy, you already know that. Okay, I need not explain it. So if you want to compare it, you want me to explain, I can do that. Simply what I have to do is I just have to copy this block diagram, so it will be easy for me to explain. So I'll explain it. So you can see this is u of t, this is x dot of t near the summing point. So that's why I written here x of t here. Put a dot and write x of t. So here at near this summing point y of t is there. Okay, just join all the points. Okay, this point, and this point, and you can see from x of t to x dot of t there is a. So give a signal, just give a connection and write a, and whatever arrow mark you can see from x of t to x dot of t arrow mark is there. So put this arrow mark. From x dot of t to x of t there is an integral. So write integral here, integral d of t, and put an arrow mark. From u of t to this x dot of t there is an arrow mark. So put this arrow mark like this. From x of t to y of t there is arrow mark is in this direction. Put this arrow mark, and from u of t to y of t this d is there. So from u of t to d of t, y of t, sorry, not d of t, u of t to y of t, put an arrow mark and write d. Okay, so just compare these two, you will be easily able to understand how to draw the signal flow graph. I hope you already know how to draw the signal flow graph from the block diagram. So let us see. So next let us see the selection of the state variables. So if you want to select the state variables, the state variables of a system, they are not unique. Okay, so there are many choices for the given system to select the state variables. So but there are some guidelines which are to be followed for the state variables selection. Okay, first thing is, for a physical system, if there is a physical system, then number of state variables needed to represent the system, they should be equal to the number of energy storage elements. As I have already told you, this I have already discussed. So number of state variables must be equal to the number of energy storage elements if it is a physical system. Okay, that is one guideline. Okay, next is, if there is if the system, okay, if you are representing it by linear constant coefficient differential equation, okay, if you are representing a system by a linear constant coefficient differential equation, then the number of state variables needed, okay, to represent the system must be equal to the order of the differential equation. Okay, so if a system is represented by constant coefficient differential equation, okay, so if a system is represented by linear constant differential equation, I'm unable to see my cursor, so I will take laser. Okay, so if a system is represented by a linear constant coefficient differential equation, then the number of state variables needed will be always equal to the order of the differential equation. And one more guideline is, if a system is represented by a transfer function, if a system is represented by a transfer function, then the number of state variables needed then the number of state variables needed where is it? Yeah, then the number of state variables needed to represent the system, it must be equal to the highest power of s in the denominator of your transfer function. Okay, so the number of state variables will be equal to the highest power of s in the denominator of your transfer function. So these are the three guidelines that are to be followed for selecting the state variables for the given system. Okay, now let us see the state space model of RLC circuit. Okay, state space model of RLC circuit. Now let us consider RLC circuit. Okay, and let us assume Vi of t is our input, and let us assume I of t is the current flowing into the circuit due to this input voltage. Okay, and it is our V0 of t, which is the voltage across the capacitor. Okay, which is the voltage across the capacitor. So now you just first of all check how many storage elements are there here. So if you observe here, one inductor and one capacitor is there. One inductor and one capacitor is there. That means what? There are two storage elements. So how many state variables will be there? There will be, sorry. So there will be how many state variables will be there? Two state variables. Why? Why? Because there are two storage elements. There are two storage elements. Therefore, number of state variables are 2. Okay. So these two state variables are what? One state variable is due to the current flow through this inductor. Okay. And another one is voltage across the capacitor. So here all the elements are connected in series, isn't it? All the elements are connected in series. Therefore, what is the current in the inductor? Current will be same. All the elements are connected in series means current in all the elements is same. So what is the current in inductor? I of t. So what is the voltage across the capacitor? V0 of t. So what are our state variables here? I of t and V0 of t. Okay. State variables are 2. What are those state variables? I of t is one state variable. Other one is voltage across the capacitor is another state variable. Okay. So what is our output here? Output is V naught of t. So V naught of t is nothing but Vc of t, isn't it? What V naught of t is nothing but Vc of t. It is the voltage across the capacitor. V naught of t is the voltage across the capacitor. So you can write Vc of t or V naught of t. So what is output notation in state space analysis? Y of t is the output notation. So Y of t is equal to what? V naught of t. That is equal to Vc of t. So now apply KVL across the loop. Apply KVL across the loop. If you apply KVL across the loop, then what do you get? I will just copy the circuit here. Okay, I will copy the circuit. So now you just apply KVL across this single loop circuit. So what is it? If you apply KVL, what is Vi of t? That is Vi of t is equal to what? R into I of t plus L into di by dt plus Vc of t or V naught of t, whatever. Okay, so I have written Vc of t, voltage across the capacitor. Now, what is I of t? I dot of t. We want the state equation, isn't it? State model. We want state model means we need state equation and output equation. So state equation is what? It is the first order differentiation of the state variables. So we have two state variables here. One is I of t, another one is voltage across the capacitor. So the state variable state equation is what? I dot of t, that is d by dt of I of t. Okay, that is equal to what? You just take the differentiation of your current equation. Okay, you just differentiate. Okay, so already we have the equation here. So already d by dt of I of t term is there here. So rearrange the above equation. So what do I want? I want d by dt of I of t, because this is my state equation. Okay, so this is one of my state equation. So that is nothing but d dot of I dot of t. I dot of t is nothing but d by dt of I of t. D by dt of I of t is my I dot of t. So that you will get d by dt of I of t from the above equation. So what is it? Vi of t minus Vc of t, isn't it? Minus Ri of t whole divided by L. So what I have written here is minus R by L I of t minus 1 by L Vc of t plus 1 by L Vi of t. Okay, I have sent all this term to the left side. I have kept this on the right side, which I have written in the reverse way in this slide. Okay, so I hope you have understood. Nothing. I didn't do anything. Simply I have rearranged the terms, and from this equation I have determined d by dt of I of t. Now what is the voltage across the capacitor? Vc of t is 1 by c integral I of t dt. So if I differentiate with respect to time the above equation, what do I get? Vc dot of t, that is d by dt of Vc of t, is nothing but you just differentiate it. You will get I of t by c. Okay, if you differentiate the above equation, you will get I of t by c. So if you are writing, just write it quickly, or you just write it down later. Okay, now what are the state variables? Okay, so state variables or state vectors. What are our state vectors here? There are two state variables are this. One is current and another one is voltage. So you can write in vector form as cursor, yeah. So this is the state vector. X is equal to what? X of t, two variables are there, I of t and Vc of t. Okay, so what is different? Just take the differentiation of this. If you take the differentiation, what is it? First order differentiation, x dot is equal to d by dt of I of t and d by dt of Vc of t. Okay, so here two variables are there, two storage elements, two stored variables. Those are I of t and Vc of t. So x is equal to I of t, Vc of t, and x dot, that is d by dt of x, is d by dt of I of t, d by dt of Vc of t. Okay. Now let us arrange these differential equations in standard form of state space modeling. So what is the standard form? X of t should be equal to what? It should be the function of x of t means x dot of t, d by dt of x of t. So it should be the function of x of t and u of t, that is input. Okay, so just I'm changing the slide. So what is x dot of t? That is d by dt of x of t is it is equal to what? D by dt of I of t and d by dt of Vc of t. That is equal to what? Okay, that is equal to whatever equation that you have got. Whatever equations for current equation, what is it? This is the current equation. So you just see here. Okay, so coefficient of I of t is here minus r by L. Okay, minus r by L is coefficient of what is it? Coefficient of I of t. Coefficient of I of t is minus r by L. Okay, so other term is here minus 1 by L is also there. Vc of coefficient of Vc of t is minus 1 by L. Okay, that you have to write it. And if you go to v dot of t, that is d by dt of Vc of t, the coefficient of I of t is 1 by c. There is no Vc of t in your above equations. Better I will write both the equations here. I will copy them here so that you will be able to understand. Now see here, x dot, that is d by dt of x is d by dt of I of t, d by dt of Vc of t. So now this is our, we know the x dot of t is the function of the state variables and inputs. So what are our inputs? Vi of t is our input. Just write down Vi of t. Some coefficient we will write it later. And another state variables are I of t and Vc of t are the state variables. Okay, just write down this. Okay, I hope up to here you can write this and this. So only one input is there, Vi of t, just write it. And we have two variables, state variables, I of t and Vc of t, just write it. Okay, now go to the equation, this equation. In this equation, you just observe. Okay, you just observe here. So here I of t is there and Vc of t is there. Okay, here what is there? I of t and Vc of t. Okay, I of t. So what is the coefficient of I of t? Minus r by L. Just write down minus r by L. What is the coefficient of Vc of t? Minus 1 by L. Minus 1 by L. Okay, that is it for this equation. Next equation, another equation is here. Okay, next equation, v dot of ct. What is the coefficient here for I of t? 1 by c. So write 1 by c. What is the coefficient of vc of t? Here there is no vc of t term, so write 0. Next, what about the input? Okay, so here what is the input coefficient? 1 by L for vi of t, 1 by L. Is there any other term? No, so just write down 0. Okay, so in this equation, here, in this equation, so there is no input term. Only I of t is there, vi of t is not there. So, since vi of t is not there, just write 0 here. Okay, so simply I hope you know how to represent equations in matrix form. That's what I have done here. Similarly, what about the output? Y. Y is what? Y is the function of, Y is the function of what? It is the function of state variables and it is the function of state variables and the input, isn't it? It is a function of state variables and the input here. So, but if you observe here, what is output? What is our output here? One second. What is our output here? Our output is only the voltage across the capacitor. Output is only the voltage across the capacitor. So, see here. This is the voltage across the capacitor. Okay, only voltage across the capacitor, that's it. So Vc of t is one of the state variables we already know. So y, where did I write? Yeah, here I have written y of t is what? It is equal to Vc of t, that's it. Okay, so Vc of t is what? State variable. Okay, where is the input? Is it function of input here? No, according to this circuit, output is not the function of input, but is only function of one of the state variable, that is Vc of t, that is V naught of t. Okay, just see here, output is only function of Vc of t, that is V naught of t. Okay, so what is the coefficient of Vc of t? It is 1. Okay, so y of t is equal to only coefficient of Vc. What about the current variable? Is there current out across the output terminals? Current is there? No, only voltage across the capacitor is there. So therefore, what is y of t? We know the state variables I of t and Vc of t. There is no I of t term there at the output, therefore 0. Our coefficient of Vc of t is 1 and input is not there, plus input is not there, so 0. So 0. Okay, so it's very simple. Okay, so if you are listening first time, it may be a bit confusing to you, but it's very simple. You just go through the equations. It's easy. So just you have to analyze and write it down. So just represent the given equations in matrix form. You will get this. Okay, so we already know. So this is our state equation. Okay, this is state equation. This is the output equation. So for the given circuit, y of t is it won't have any input term. Y of t won't have any input term for the given equation. So this is 0. Okay, this is 0 for the given equation. Okay, so here these two are the state model equations for the given system. So if you are unable to follow, later you go through the video once again, you will be able to follow. It's very simple and easy, nothing complicated. So now coefficient of this state variables is what? This. Coefficient of this input is this. Coefficient of this state variable for your output equation. Okay, this is state equation. Okay, just I will erase and I will. Okay, so this whatever you have got here, this is our state equation. Okay, this is state equation and this is our output equation. Okay, this is output equation. Now in the state equation, This is the coefficient of state variable, this is the coefficient of input variable, and this is the coefficient of state variable of your output equation. So consider, wait, I will erase all ints. So consider this coefficient of state variables as A. Okay. Consider this coefficients as B. I'm unable to write. Okay. Consider this as A. Consider this as B. And consider this as C. There is no D term here. There is no D, only A, B, C. Because output is equal to Vc of t. That's why there is no D term. If there was any input term here, some plus of something, sorry, it is C, not D. There is no D term. I was telling you there is no D term, and I wrote D term. So this is C. I'm unable to write C. Okay, this is C. Okay. So this is it. This is what I have written here. Yeah. A, B, C. There is no D, so D is equal to 0. Okay. So what I can do is, to make it more easy and to understand, I can here plus 0. Okay. This is 0. Okay. There is no Vi of t actually, but I am writing it here. There's no need to write at all. It's only equal to, it is only directly, output is only equal to Vc of t, not Vi of t. So actually I should not even write this Vi of t. Okay, I should not even write this. So this is our D. Okay, A, B, C, D are the constant coefficients. Okay, this is it. I don't know whether you are able to follow or not, but I tried my best to explain in the as simple possible way as possible. Okay. Okay then. So let us see the transfer function of state space model. So we know state space model equations. State space model equations. What are those? State equation and output equation. What is state equation? X dot of t is equal to Ax of t plus Bu of t. And output equation is Y of t is equal to Cx of t plus Du of t. Okay. So now take the Laplace transform of each term assuming 0 initial condition. If you take the Laplace transform of each term assuming 0 initial conditions, so what is x dot of t? Sx of s, and a into x of t, a is constant, x of t will become x of s, b is constant, u of t will become u of s, y of t will become y of s if you take the Laplace transform, and c is constant, x of t will become x of s, u of t will become u of s. Just write it down. Okay. So consider this as equation 1. So what is our equation 1? It is the state equation actually, which is in Laplace form. State equation in Laplace form is our equation 1. So here Sx of s is equal to Ax of s plus B u of s. So I am taking that equation. S x of s is equal to A x of s plus B u of s. Now send x of s term on the right side term, this term to left side. Okay, send it to the left side. So if you send it to the left side, it will become S x of s minus A x of s is equal to B u of s. Take x of s common, you will get s minus A. So here coefficient of s is some, I am assuming some identity or unity matrix is there. I am writing unit matrix. Okay, I am assuming there is a unit matrix. Means instead of writing 1, there's nothing is no coefficient of s is 1. So instead of writing 1, of course we won't write 1. So I am writing here identity matrix I, or we can say unit matrix, okay, which has ones only in the diagonal, isn't it? I hope you know that. Okay, so S I minus A. Okay, what is I is the unit matrix. Okay, so B U of S. Okay, here x of s, what is x of s now? Send this Si minus A to the right side. Si minus A inverse B U of s. Okay, now substitute x of s in our equation number 2. What is our equation number 2? Y of s is equal to C x of s plus D U of s. So x of s, substitute in that, you will get y of s is equal to C into Si minus A inverse B U of s plus D U of s. So here I, as I already told you, it is our unit matrix. So this is what you will get. Okay, now where is it? Yeah, y of s is equal to what? C into I minus A inverse B U of s plus D U of s. Now further you just simplify it. Okay, take U of s common. You just take U of s common, you will get y of s equal to C into Si minus A inverse B plus D. Okay, so replace this whole term by some notation G of s. Okay, so y of s is equal to G of s U of s. So what is the ratio of Laplace ratio? Y of s is the output, U of s is the input. So y of s by U of s is nothing but G of s, that is equal to what? C into S minus I minus Si minus A inverse B plus D. Okay, so this G of s is nothing but transfer function matrix. Okay, G of s is the transfer function matrix. Are you able to follow or not? Okay, let us see, go through some numerical problems and let us conclude this topic. So here, let us consider an electrical circuit. Okay, and you have to represent it by a state model. So state model means what? It should consist of a state equation and output equation. So this is the electrical circuit given. So here if you observe, the number of storage elements in this given circuit, how many storage elements are there? How many are there? 1, 2 and 3. Okay, there are 3 storage elements. 1, 2 and 3. 3 storage elements means how many state variables? Total 3 state variables. Okay, 3 state variables. If I start writing, it is wastage of time. State variables. Okay, number of storage elements is equal to number of state variables. My cursor won't listen to me. So total 1, 2 and 3 storage elements are there. So there will be 3 state variables. Okay, so what are those state variables? We can just assume current due to L1, current due to this inductor L1, I1, and next current due to inductor L2 I2, and what is another one is voltage across the capacitor C. So what are the state variables? I1, I2 and Vc. Okay, the state variables are I1, I2 and Vc. Okay, and we know what is the notation for state variable. Notation for state variable is X. Okay, notation for state variable is X. Okay, X is the notation. So what is I1? I1 is equal to, let us assume, X1. I2 is equal to what? X2. Vc is equal to X3. So since three storage elements are there, three state variables will be there. What are those state variables? I1 and I2 and Vc are the state variables. Current due to inductor 1, current due to inductor 2 and voltage across capacitor. Okay, and we know state variables are denoted by X. So since they are denoted by X, therefore I1, let us assume I1 is equal to X1, I2 equal to X2 and Vc is equal to X3. Okay, so we can represent it in the circuit diagram. This is our circuit. So we just represent it in the circuit diagram. So I1 of t, I2 of t and Vc. Okay, now there are two loops in the given circuit. I have assumed loop 1 and loop 2, and in the question itself they have mentioned this as y of t. Y of t means what? Y of t means output. Y of t means what? Output. Y of t means output. I'm able to write P. Okay, whatever. Now let us apply KVL in loop 1. So if you apply KVL in loop 1, so you can see here input is u of t. So u of t minus, okay, u of t, okay, so here this okay, these three elements are in one branch and this element is another branch. Okay, so I will start with this inductor. Whatever I have written, same equation I will tell you. L1 into di1 of t by dt plus R1 into I1 of t, R1 into I1 of t, L1 into di1 of t by dt plus u of t minus Vc of t. Okay, total 4 elements in this loop is equal to 0. So here instead of writing Vc of t, what is Vc of t? Vc of t is nothing but X3, isn't it? Vc of t is nothing but X3. So instead of writing Vc of t, what I have done is in the next equation I have written X3 of t. Okay, instead of writing Vc of t, I have written X3 of t. Same equation, L1 into d by dt of x1 of t, R1 x1, here also, instead of writing I1 of t, I have written x1 of t, u of t as it is I have written, Vc of t I have written X3 of t. So these two terms, okay, I will just highlight them. So I1 of t, it has been replaced by x1 of t, Vc of t is replaced by X3 of t. Okay, so instead of writing d by dt of x1 of t, I can write x1 dot t. Okay, L1 into x1 dot t plus R1 x1 of t, u of t, X3 of t equal to 0. So what is x1 dot of t? Just what is it? You just send all these terms to the right side and divide by L1. So what do you get? X1 dot of t is equal to minus R1 by L1 x1 of t plus 1 by L1 x3 of t minus 1 by L1 u of t. So you can see here, this is our state variable, okay, equation, and this is our input equation, input term. So x1 dot of t is the function of what? State variables and the input variable. So here this is our state variable terms and these are our input terms. Consider it as equation number 1. Okay, consider it as equation number 1. Now let us go to loop 2. This is our loop 2. So what are all the terms are there? Vc of t is there, L2 is there, and R2 is there. So what is it? L2 di2 by dt. What is the current here? I2 of t, isn't it? So L2 into di of 2 by dt plus R2 into I2 of t minus Vc of t is equal to 0. Okay, you know KVL, apply KVL in loop 2, L2 into di of 2, I2 of t by dt plus R2 into I2 of t minus Vc of t is equal to 0. Now here you can replace I2 by x2 of t and Vct by x3 of t. Okay, and d by dt of x2 of t you can rewrite it as x2 dot of t. So L2 into x2 dot of t plus R2 x2 of t minus x3 of t. So from this you will get x2 dot of t is equal to minus R2 by L2 x2 of t plus 1 by L2 x3 of t. Consider it as equation number 2. Consider it as equation number 2. Now let us go back. Let us go back to this circuit. So here I have even assumed the nodal voltage. Vc of t is my node voltage. Only capacitor is connected here. So Vc of t is my node voltage. Now let us apply KCL at this node. KCL at this node. So what is it? Let us assume all the currents are leaving. All the currents are leaving. So I1 of t plus current flowing to this capacitor, some I3 of t plus I2 of t. Okay. So what is I1 of t? I1 of t is x1 of t. What is I2 of t? x2 of t. Plus what is the current through the capacitor? C into dVct by dt. What is Vct? It is x3 of t. So I hope you have understood. I have applied KCL at this node. All the currents I have assumed are leaving. So what are all the currents? I1 of t plus I2 of t plus I3 of t. I3 of t is the current through this capacitor. What is the current through the capacitor? C into dVct by dt. Okay. So just replace I1 of t, I2 of t and Vc of t by x values. So that is it. So applying KCL at node Vc of t. So what is it? I1 of t plus I2 of t plus current through the capacitor C into dVct by dt. So what is I1 of t? Replace it by its variable x1 of t, I2 of t, x2 of t, Vc of t, replace it by x3 of t. Okay. So if you replace it by x3 of t, you will get this equation. So what d by dt of x3 of t means? You can rewrite it as x3 dot of t. So determine x3 dot of t, you will get x3 dot of t equal minus 1 by c x1 of t minus 1 by c x2 of t. Consider it as equation 3. Now rewrite all the terms. Okay, whatever 3 equations are there, you write them in matrix form. You will get the state equation. Okay, you will get the state equation. So these are the coefficients of x1, x2, x3, and for u of t, these are the coefficients. So u of t is there only in how many equations? Only one equation, I think so. In equation x1 dot of t, u of t is there. In second equation, u of t is not there. In third equation also, u of t is not there. That's why you have got only one coefficient value minus 1 by L1 of. So this is our state equation. Simply from equation 1, 2 and 3 you can write down easily. You might be already knowing how to write the equations in matrix form. Now what is our output? What is output? Let us go to this circuit. What is our output? Yeah. What is y of t? Y of t is what? Across R2. Y of t is across R2. Okay, y of t is across R2. Okay, so it is the voltage across R2, we can say. Y of t is across R2 means it is the voltage across R2. So what is the voltage across R2? R2 into current flowing through R2 is I2 of t. So R2 into I2 of t. What is I2 of t? It is x2 of t. Okay, so it is x2 of t. So I have written here. Yeah. So you can see y of t is what? R2 into I2 of t. So instead of I2 of t, you just write x2 of t. So R2 x2 of t is our y of t. So now only I2 term is there, means x2 term is there. What about the other variables? X1 and x3 are not there. Therefore 0, 0. What is the coefficient of x2? R2. Write it here. Plus, what about here? Input is not there. So 0, 0. What is our input? Vi. What is our input? What is our u of t? Yeah. So here our input is u of t. So write u of t. 0 u of t. So no need to write input is not there. So therefore no need to write u of t. Okay. So very simple. It's very simple. This is our output. This is the coefficients of the state variables. Okay. So these are the state equations and output equations. So together they constitute what? State model of the system. So we have got the state model of the system for the given electrical circuit. Okay. For the given electrical circuit, we have got the state model of the system.